Chapter 15 is really just an extension of everything we learned in Chapter 14 with a much cleverer title. Probability rules! In the last chapter, we were only adding probabilities when we had two events that were disjoint. Now remember, disjoint means that the events can't happen at the same time. In other words, they're mutually exclusive. In the Venn diagram, we had two circles that had no overlap at all. Now in this chapter, we're changing it a bit. We're saying that we can add overlapping events or events that are not disjoint. That's represented by this Venn diagram here. And to do that, we have to change our addition rule. So it's no longer just probability of A plus the probability of B, because if we added these two probabilities, we see that we would count this middle section, this overlapping section, 2 times. So to counteract that, we add probability of A with probability of B, and then we subtract out that overlap. We're subtracting out the double counting of A and B, and that gives us the probability of getting A or B. In this example question, we're going to be randomly selecting a page from the book. Based on a representative sample, we have the following statistics. 48% of pages have a display, 27% of pages have an equation, 70% of pages have both. So when we're presented with information like this, we want to go back to kind of one of the core tenets from Unit 1, which is to make a picture of our data. Now I just grabbed this from a scan of my notes, but let me explain how we fill this in. To start off, we always want to draw these overlapping circles and fill in the overlap of 7%. Now if we look at the display circle, we know 48% have some kind of display, but 7% of that is in the overlap. That leaves 41% only on the display side. Do the same thing with the equation. 7% of the 27% in that equation circle is in the overlap, leaving 20% in the equation part of the circle. Add those all up and we get 68%. 32% is outside of both circles, meaning they have neither a display or an equation. So what's the probability that a randomly selected sample page had neither a display nor an equation? 32%. What's the probability that a randomly selected sample page had a data display but no equation? 41%. I'm going to skip including the actual image of the Venn diagram in the notes and allow you to draw it on your own. But I will give you the answer to these 3 questions here, revealed in 3, 2, 1. So the probability a DWI suspect is given a test is 92%. A blood test or a breath test, but not both, is 70%, and neither test is 8%. Now, way back in Unit 1, we talked about conditional probabilities. This is a probability where we have some kind of given. It's telling us something that restricts the sample space of our overall probability. When we look at this notation here, this is saying find the probability of B given A, or in other words, find the probability of event B given event A has already occurred. Now there's an actual probability equation that we can use for this. So the probability of B given A is equal to the overlap of A and B divided by the probability of A. Whatever the given is going on the bottom of the equation in the denominator there, and the overlap goes in the numerator. So this leads us back to the multiplication rule. Last chapter, when we were multiplying two events, they were independent. We could just multiply the probability of A with the probability of B, and that was our answer. Now, when we have events that are not independent, one is affecting the other, and we have to take into account how it's affecting the second event when we do that multiplication. So the probability of A and B is the probability of A times the conditional probability of B given A. Okay? Or the reverse of that, probability of B times the conditional probability of A given B. Let's give a quick, easy to understand example. Let's say we're drawing cards from a deck and we want to find the probability of being dealt 4 aces in a row. We draw the first card, we see it's an ace. The probability of that was 4 out of 52. But now that that ace is gone, we have a conditional probability for the next card. Now there's only 3 aces left, and now instead of 52 cards, there's 51. These are not independent events. These probabilities are changing with each card we draw. They're dependent. So the second and every subsequent event would be conditional on the previous one. So we just talked about independence and how that means when we have 2 events, each event is not affecting the probability of the other occurring. We also talked about when events are disjoint, that means they can't happen at the same time. Now, at the very end of last chapter's notes, we mentioned that disjoint events can't be independent. And the reason for that is that when we have disjoint events, if we know that one occurs, we automatically know that the other event did not occur. Now, that's kind of confusing, but here's an attempt to make it a little easier to understand. Right? If we flip a coin, normally we have a 50% chance of getting either heads or tails. Those are disjoint events. We can't get both. So if I were to tell you I flipped a coin, you would guess and you would have a 50% chance of being correct. Now, if I were to tell you that I didn't get tails, you know for sure that I got heads. The probability of me getting heads is no longer 50% because these events are disjoint. They're not independent because knowing something about that first event tells us everything we know or everything we need to know about the second. Same information as before, but this time instead of doing a Venn diagram, we're going to organize this information into a contingency table. So before I go ahead and paste it from my version of the notes, attempt it on your own. Hopefully you came up with something like you see here. So question B, what's the probability that a randomly selected sample page with an equation also had a data display? Now this is giving us a given, a condition, and it's telling us that the page we selected has an equation. So we're looking specifically at the 27% of the pages that have an equation. Of the 27% that have an equation, what percentage also have a data display? 7% out of those 27%, that is going to give us our probability of 0.259. C, are having an equation and having a data display disjoint events? No, they're not, because they can occur at the same time. 7% do occur at the same time. And lastly, are having an equation and having that data display independent events? This one's a little more difficult to explain. Now we can test independence mathematically using this equation down here on the bottom. Does the conditional probability of B given A equal the same thing as just the overall probability of event B? Now, in other words, we have some event, in this case event B. Is that the same as the probability of event B after A has occurred? Is event A affecting the probability of event B? So let's apply it up to what we did in part B here. Okay, so to start off, event B is the display, probability of getting display. And event A is the probability of picking a page with an equation. So to start off, let's just define what the probability of picking a page with a display. I can't highlight very at the bottom of the slide there. That's why I'm always right above it there. So the probability of highlighting a page or of selecting a page with a display is in this top row here, and it's 48%. Now the question is, if we're given some kind of condition. In this case, we're being told that the page has an equation. Is that affecting the probability that it also has a display? And the answer is yes, it is, because once we're told it has an equation, we're restricting our sample space to just the 27% of pages that have equations. And of those 27%, only 7 of those percent have equations. That's what we did in part B, which gives us a probability of 0.259. This is different than the overall probability of a page having display. That means A is affecting B. Okay, in this case, the probability of a page having an equation is affecting whether or not it also has a display. These are not independent events. In addition to Venn diagrams and contingency tables, we could also make a picture for a probability problem using a tree diagram. And a tree diagram is exactly what it sounds like. We lay out all our probabilities and they branch off, leaving us with something that looks like a tree. So here we have a problem where we asked a number of college students about their drinking habits and whether or not they were involved in an alcohol-related motor vehicle accident. So to start off, we have all of our subjects at the left side here, and they're split into 3 options according to their drinking habits. We have the students who identified as binge drinkers, moderate drinkers, and then those who abstained from drinking entirely. Notice that all of these probabilities add up to 100%, and that's going to be the case along every
branch of our tree. So for example, when we go up along this binge branch and we come up here, they're then asked, were you or were you not involved in an alcohol-related motor vehicle accident? Okay, 17% were involved in one, 83% were not. Those total 100%. Same thing for this branch down here and the branch of the abstainers. Okay, now at the end here, the right, these are all disjoint events. Okay, so every student falls into one and only one of these categories. They have to add up to 1, and the way we get these numbers is by multiplying all the branches that we take to get to that path. So 0.075 is the product of 0.44 and 0.17. Okay, we can use a tree diagram to add probabilities to find compound events. It's actually a bit easier to find conditional probabilities in some cases when we're looking at a tree diagram. If we're lucky enough to have this created for us, we can answer questions very quickly. We also could create it on our own. So what's the probability of a randomly selected student being involved with an accident and being a moderate drinker? We just follow that path down the tree. We see here this event is a moderate and accident, so the answer to that question is 0.033. Number 2, find the probability that a student was involved in an alcohol-related accident given that they were a moderate drinker. We're only looking at the branch of moderate drinkers. Okay, we don't care about this whole top branch or this whole bottom branch. Of the 37% who are moderate drinkers, 9% were involved in a motor vehicle accident. Lastly, this is the difficult one. Find the probability of a student being a moderate drinker given that they were involved in an accident. Now, there's a bunch of different branches here where students were involved with accidents, and we have to take all of those into consideration. If we add all 3 of those probabilities up, we get 0.108. That's the condition for problem number 3, is that we're choosing a student from the pool of all the students that were involved in an accident. And there's an overall probability of 10.8%, 0.108, that a randomly selected student will have been involved in an alcohol-related accident. Now, of those 10.8% of students, what's the probability that we pick one who was a moderate drinker? So in other words, given they were involved in an accident, find the probability that they were a moderate drinker. If we apply all this to the conditional probability equation down at the bottom here, we can see that the given goes to the bottom, that's the 0.108. The overlap goes on the top, overlap being 0.0333, and then we can just divide to get our answer, 0.306. So while a lot of the questions on the AP test might be a bit hard to decipher, this one is particularly scarce, and I think I probably deleted a bit too much to keep it on the slide here. So to fill in a few of the blanks, we are examining the proportions or probabilities of freshmen going to public schools versus private schools, and then those who go on to graduate versus not graduate. So use that information to try to make a tree diagram out of these percentages along with the ones that aren't listed, but you can kind of figure out from the ones that are given. And hopefully you came up with something like the display here. Now we want to use this tree diagram to answer the following questions. First, is there any evidence that a freshman's chances to graduate may depend on what kind of high school the student attended? In other words, are high school and graduation dependent or independent? And then B, what percent of freshmen eventually graduate? So for A, the answer is yes, it does depend on the high school, so these are not independent variables, and we can see it on these 2 branches here. Those who attend public school have a 75% chance of graduating, while those who attended private school have a 90% chance of graduating. Those are different. It's probably more than we would expect to see by chance, so you're more likely to graduate having attended private school. B, what percent of freshmen eventually graduate? We would take the 0.525 of those who went to public school, add the 0.270 who went to private school, and we get 0.795.